for example, a sandbox exception sometimes appears, and it's impossible to understand what's wrong because many times there actually is nothing wrong. The GUI and the script are both okay, but the memory of gmat has somehow become corrupted. So there's one trick that will sometimes fix your error, which is to save twice, once from the GUI and once from the script. So you can do that by clicking save here, then opening the script and choose save and sync. I already have the script open. Okay, and that has the effect somehow cleaning out the memory. So yeah, my suggestion is if you have such an error and you can't figure out how to fix it, then try this before you close the program and lose the work that you've done. Okay, I mentioned already that MATLAB can be integrated with GMAT, but we're not going to do it here. Right, so now let me close the script and we'll begin adding some resources that we're going to need before we create a simple mission. Okay, so one resource you're always going to need is a spacecraft. Use the right mouse button to select Add Spacecraft from the menu, the only option. That creates Spacecraft 1. When you double-click on some resource or mission event in GMAT, it opens up a Properties window. So we double-click on Spacecraft, we see that it has, well, quite a lot of properties. There are many tabs here, like power systems and fuel tanks that we won't use, at least not right now. But the Orbit tab, the default selection, is important, and we'll always want to change some things in that. One thing I recommend changing right away is the epoch format so that you know when the mission is beginning. Moduling format is not very intuitive, but UTC Gregorian is. It gives you a date and a time. So now we see that this mission is going to begin on the 1st of January, the year 2000, in the middle of the day. That's a long time ago, but the year 2000 is special for GMAT because these coordinate systems also have 2000 in the name, which means that they are measured with respect to the Earth's axis in the year 2000. So certain things are a little bit more accurate in that year because since then the axis of the Earth has drifted a little bit. You'll probably also want to change Cartesian state type to Keplerian. Cartesian means that you give the initial conditions of the spacecraft as positions, x, y, and z, and velocities, vx, vy, vz. Which is fine, but usually we describe orbits in terms of their Keplerian parameters. If you change that, you see the equivalent of those initial conditions in terms of the semi-major axis, eccentricity, inclination, right ascension of the ascending node, argument of perigee, and true anomaly. Okay, so you'll probably want to make those two changes, and today we're going to add orbit parameters that correspond to the Hubble telescope. So the semi-major axis, 6917 kilometers. Now the distances are measured in kilometers by default. Eccentricity, a very small value of 0.00028, and an inclination of 28.5. RAN of 80.3, argument of perigee of 65, and true anomaly of 0. Okay, once you've made those changes, apply will apply them, OK will apply them, and close the window. I repeat that these are just the initial conditions of the spacecraft. But they do not get updated automatically once the spacecraft moves to another point. It's at that new point, but these remain the same values because they correspond to its initial conditions. All right, click OK. And since this corresponds to the Hubble, it makes sense to rename it Hubble. Okay, so we have a simple spacecraft, or one spacecraft. The outputs that were there by default are probably things that you'll want. The orbit view is a three-dimensional plot, and ground track plot is one showing the ground track. So again, those were there by default. Let's add them back. Double-click on orbit view, and you can see a variety of things that you can change in the plot. You can show or not constellations. You can add third bodies. For example, we could add the moon and the sun. We're not going to see them unless we zoom out a lot, but if you have a large orbit, you can see other bodies in the solar system. The most important thing here is to select the spacecraft that you want this plot to show. By default, it's going to select the first spacecraft. And since we only have one, that's fine. It's automatically selected. If there were more, they would be here in the list, and you select them with this arrow. You can also change the viewpoint vector and direction. I don't usually do that because it's easy to change those things with the mouse once it's created the plot. All right, so I click OK. The ground type plot has fewer options, but again, the most important thing is to select the spacecraft that you want to see. It will always select the first thing in a list by default, but when you have more than one spacecraft, you need to select them actively so that the plot is showing what you want it to show. Okay. And finally, one thing which was also there in the default scenario that you're going to need as long as the spacecraft moves is a propagator. So click on the propagator um, folder and add propagator. Creates propagator 1. When you double click on that, you see its properties. So configuring a propagator is one of the most important things that we do in the course. I usually ask something about that in the final. First, let's configure the numerical integrator. Actually, the default integrator is fine. If you never want to change this, that's acceptable. It will work just fine. But the authors in the user manual suggest Prince Dorman 78, which is another Runge-Kutta type method, and changing minimum step size to 0. So I usually do that, but again, that's optional. On the right-hand part is more important. You have to select the forces that gmat will apply. You select the central body, right, center of the orbit. The primary body usually is the same thing, and the primary body can be expanded in terms of spherical harmonic perturbations. So there you choose the truncation points of a gravity model. Okay, so you know the Earth is not exactly spherical. The deviations from a perfect sphere are captured by these terms in a spherical harmonic expansion. Some of them have names, like J2 and J3, but some don't. Okay, so if you want to treat the Earth as a point mass, that is with no perturbations, you would put degree 1, order 0. The order must be less than or equal to degree. If you want to consider the point mass and the J2 term, you would put degree 2, order 0. If you want also to include J3, then it's degree 3, order 0. The degree is the number of perturbations in the north-south direction, and order is the number of terms in the east-west direction. So they don't have names like J2 and J3, but they can be important in some orbits. And again, it always has to be less than or equal to degree. Okay, so again, remember these are truncation points. For example, this selection considers the point mass term, J2 term, and J3. It's impossible just to consider J3. And it would make no sense because it's much smaller than J2. Okay, so for this propagator, we're going to consider degree 2, which is J2, and order 0. And we're going to add 2 point masses. For most orbits, the moon and the sun have some effect, much larger than the other planets. So we'll add those as third bodies by clicking select here, and then sun. By the way, in GMAT, you almost always have to select things with an arrow. You move it from one list of available options to selected options. Okay, so we'll add the sun and the moon. Click OK. And then this is a propagator which considers 3 perturbations, the J2 effect, the moon, and the sun. Okay, you can add atmospheric drag here. We won't today. Solar radiation pressure, relativistic corrections. Okay, none of that we're going to use right now. All right, so click OK. And since this propagator considers J2 as well as the moon and the sun, I'm going to call it prop J2. Okay, again, if I'm going too fast, just say so. Now we have a spacecraft, a propagator, 2 outputs, and we can make a simple mission which propagates the spacecraft forward in time. So I'm going to add one mission event to the mission sequence with append propagate. Let's look at the default options for this propagate. You can see that, well, by default, it's going to take the first propagator. Right now we only have one. The first spacecraft, that right now we only have one. And the stopping condition is going to be elapsed seconds equal to 12,000. That's just an arbitrary default selection for gmat, but it says that this propagate event will propagate the spacecraft forward using this propagator and its forces until the stopping condition of 12,000 seconds has been completed, then it will stop. Okay, so stopping conditions are important. You can add more than one. For example, I could add altitude equal to 20,000 kilometers. Now I have two stopping conditions, one for the time being 12,000 seconds, one for the altitude being, well, I wrote here 2,000. Fine, it doesn't matter, because this stopping condition won't be satisfied. We're in an orbit of approximately a bit less than 7,000 kilometers. The altitude could be 2,000 if we added atmospheric drag and the energy of the orbit slowly decayed. But since we don't have that, it's not going to decay, and it will never reach 2,000. So putting this stopping condition by itself would allow this event to continue forever. Having both of them, this one has no effect at all. Okay, so generally you have one stopping condition. You can put multiple ones, but remember that they are connected by OR logic, not AND logic. When you finish the event, one of the stopping conditions will be satisfied. The first one that was satisfied will cause it to stop, and the rest will not be satisfied. So you cannot enforce multiple things through the stopping condition. Okay, so in the end, I didn't change anything here. I'm going to leave the default stopping condition. Click OK, and let's run this mission with the run button, which looks like play up here at the top. So when we run it, we see the two outputs, which are two plots, this three-dimensional view. With the left mouse button, you can change the viewpoint, the view direction. With the right mouse button, you can zoom in and zoom out. You can animate the mission, that is to play it without redoing the calculations, and control the speed. So it often happens too fast. If you click slow animation a few times and then play, you can see the spacecraft move around a bit slower. You can see that it went around approximately twice here. Okay, the ground track plot is here. Similar thing, if you want to animate it, you can click animate and you see the projection of the spacecraft on the Earth's surface and the ground track plot. Okay, so again, those things that we've just added now are basically all there by default. We changed the initial conditions of the spacecraft, but we added the propagator and two outputs that are going to be there by default. We did change the configuration of the propagator as well. Okay, there are other outputs that are more specific that you're going to need to create, which are called XY plots. So in output, add an XY plot. And in an XY plot, you define which variables you want to see on the X and Y axes. On the X-axis, click Edit X, and let's change the default variable to elapsed seconds. And the default Y variable is going to remove the X coordinate of the spacecraft, which is selected by default, and you remove it with the left arrow, by the way, and add the RAN and true anomaly. Okay. Okay, so we created a two-dimensional plot that will plot versus time, the RAN, and the true anomaly, which are both angular variables. In GMAT, angular variables are always measured in degrees. Right, and click OK. Once we've created this new plot, we won't see it until we run the mission again. So let's do that. And we see this new plot, which has the RAN in red and true anomaly in green. So first, let's look at the RAN. The RAN should change a little bit, but because we have perturbations in this propagator, right? We have J2, the moon, and the sun. Any of those by itself is enough to make this orbit no longer closed, and the orbital parameters will drift. So we see that the RAN does indeed drift. It's not a big change, but it is changing slowly in time. The true anomaly is strange because this is a nearly circular orbit. Right? Remember that the eccentricity here is almost zero. So the true anomaly should be changing almost linearly. It's the angle of the orbit, and the velocity of the orbit is constant, so it's moving around at a constant angular velocity. However, it doesn't look like that. stays near 345, gets to 360, jumps to 0, stays small, jumps again. The reason it has this strange behavior is because gmat is having a hard time defining the true anomaly, precisely because the orbit is almost circular, and that means that it doesn't really have a perigee or an apogee. They're not well defined. And since the true anomaly is measured with respect to the argument of perigee, it's also not well defined. Okay, so I'm going to use that problem here, even though it's not, say, such an important thing. It's more numerical than anything, but to illustrate how to do various things by fixing this plot. Okay. One thing you can do in gmat is play around with the propagator to look at the effect of different perturbations. Here, we could guess that the J2 perturbation is the one that makes it difficult for gmat to calculate the perigee correctly. Remove J2 by changing degree from 2 to 1. And then if I run this again, then we see that the true anomaly behaves in a much better way. So in this case, gmat is able to locate the perigee and its consistent location, and therefore the true anomaly is behaving in a consistent way too. Okay, but if we add the J2 perturbation back, that changes the orbit enough that it's hard for gmat to locate perigee. Okay, so as I said, we'll come back to this plot and change it in various ways. Another kind of output that you'll want to use in gmat is a report file. Basically, there are two different ways you'd want to use that. One of them is to simply save the data of a mission. For example, if we want to analyze this data in another program like MATLAB, we need to somehow import that data. So a report file is a text file where you can save data that you can import into another program. So let's add a report file now. Open the report file. And here you define a list of parameters. These are things that will be written to that report file at every time step of the mission. Okay, so let's change this parameter list to include the same three things that we're showing in this plot. So first remove the two things that are there by default. Find elapsed seconds. By the way, if you click on this list of predefined variables and begin typing, like EL, it will jump down to that point in the list, right, which is what I've been doing. So select elapsed seconds, then ran, and then true anomaly. And click OK. And you see this, well, the parameters have changed here. Again, these are things that will be plotted as columns of data in the text file called report file 1. Right, so click OK. To generate the report file, you have to run the program again. Reports don't open automatically, but they're accessible from the Output tab. So find the reports folder, double-click report file 1, and you see the report file, which has 3 columns of data: elapsed seconds, ran, and true anomaly. Okay, so you could read this into MATLAB or some other program. If you want to control the resolution of this data, that's controlled mainly with the maximum step that the propagator takes. Here, the maximum step size is 27,000 seconds. If I wanted greater resolution and step sizes of no more than 60 seconds, I could change that to 60. Click OK, run it once more. And if we open the report file again, you would see that these columns of data are larger. And if we focus on two entries here, that elapsed seconds differs by approximately 60 seconds. So in essence, gmat is going to take the largest step that you permit it to take, as long as it can stay within the required accuracy. Okay, so right now I'm going to change that step size back to 27,000 so that the program is not slowed down later. Or 2,700, I mean. Okay, so we know how to make a report file, again, which is here. And the parameters that are in its definition are reported at every time step. Okay, let's begin adding some new things then. One of the things that gmat does that's very useful is to do calculations. That is, You don't have to do calculations by hand and tell it exactly what it needs to do. You can define a beginning point and an end point, a type of boundary value problem, right? You start in a particular orbit and you tell gmat that you want to go to a new orbit with certain properties. Right? Gmat can do a calculation that will tell you how much force you need to apply to get to that new orbit, or the particular point at which you need to apply the burn to get to the new orbit, and things like that. All right, so doing those calculations is a very useful thing. They're done in something called a target loop, which we'll create in just a moment. But before we can do that, we need some new resources. Okay, one resource that we need to solve this kind of problem is a numerical solver. So basically, we'll be defining a boundary value problem and ask gmat to try various values until it can find a solution. Okay, so we need a boundary value solver, which is in the submenu of the solvers folder, boundary value solvers. We add differential corrector. If we double click on the differential corrector, you see the options available for that. The Newton-Raphson algorithm is a good one. You don't need to change that. The forward difference derivative method works fine too, but I would recommend changing the maximum iterations from 25 to 100 or larger. And that's the number of iterations that this solver is allowed to take before it stops. If you put 25 and it cannot find a solution within 25 steps, it will stop. So many times that's not enough, and there's no harm in increasing that a little bit. Okay, so now we have a numerical solver, and remember that it can try 100 times to find a solution before it gives up. And now we need some way to apply the force, which is called a burn. There are two types of burns in GMAT, impulsive burns and finite burns. At the end of this introduction, there's an appendix on finite burns, so you can look at that if you want, but I don't think we will ask anything about finite burns in the practicas. In any case, a finite burn is a more realistic way of considering the finite amount of time that a force is applied. So the spacecraft moves forward as you're burning some fuel and applying a force. But the limiting case that that time is very short is called an impulsive burn. So that's the one that you've probably have most formulas for in class, and assumes again that the force is applied instantaneously, so that it instantaneously changes the velocity vector. And that's called an impulsive burn, which we're going to use now. So create an impulsive burn called impulsive burn 1. You double click on that, you see its options. You choose the coordinate system, the type, the origin, and the axes. You don't need to change these things, at least in this course. The defaults are usually what you want, but you do need to know what it means. This is a local coordinate system attached to the spacecraft, and the axes are defined by its velocity vector. So the V and B axes correspond to velocity, normal, and binormal. In the direction of the velocity vector, normal to the orbital plane, and binormal to both of those. So the third component is within the orbital plane, but perpendicular to velocity. So this would typically be a radial direction. And these three elements correspond to those three axes. If, for example, I want to apply an impulse in the direction of velocity to increase velocity of 1 kilometer per second, I could put that value here, click OK, and use that impulse within the mission. But most of the time for us, we are not going to know what the value of the impulse is exactly. We're going to ask GMAT to calculate it. In that case, it's better just to keep 0 as the initial condition for all of those elements. Okay, we don't have fuel tanks, so we don't need to worry about the decreasing mass of the fuel. And I'll click OK. So in the end, I'm not changing anything, but remember that you have to understand what the elements correspond to. Velocity, normal, and binormal. Okay, so now that we have an impulsive burn and a solver, we can create a target sequence. Okay, so let's go back to the mission. And what I want to do is apply an impulsive burn that will increase the size of the orbit to move the spacecraft to an elliptical orbit, but within the same orbital plane. I want to apply that at periapsis. So after this propagate, I'm going to insert another propagate that will take the spacecraft to periapsis. Okay. So let's open propagate 2 and configure that. This again is going to apply the first propagator, the only one, to the only spacecraft. That's not an issue. The stopping condition, however, we need to change so that it stops at periapsis. That's done by just changing the parameter to periapsis. When you click OK, then the condition value disappears. If you try to type a value, it won't allow you because periapsis is not a numerical parameter. It's a geometric point on an ellipse. Apoapsis is another one. They don't have numerical values. So if you simply select them as the parameter, gmat will stop at periapsis or apoapsis. Um, and that's it. I mentioned that because this is an exception to the usual format. The usual format of a stopping condition is some parameter equal to a particular value. Okay, so this propagate stops at periapsis, and just for good practice, I'll call it prop periapsis, peri, and we haven't saved in a while, so it's a good idea to save again too. Okay, so now we're at periapsis, and I want to do this calculation. So after this event, I'll insert a target loop. Okay, this target loop is again going to apply an impulsive burn, and the target that we need now has three elements that I'm going to add here, and then we'll talk about them. You need a vary statement, we need a maneuver event to apply the impulsive burn, and we need an achieve. This structure of the target is probably the simplest one you can imagine. We're going to tell it to vary the magnitude of the impulsive burn, apply the impulsive burn, and tell it which condition of the new orbit we want to achieve. Targets can be a lot more complicated. You can have multiple varies and multiple achieves. Okay, I want to emphasize very strongly that you should have the same number of varies as achieves. This is for making it a mathematically well-posed problem. Right? You know that if you have more variables than conditions, you'll likely have an infinite number of solutions. The contrary case, the more conditions than variables, you'll likely have no solutions. Okay, there are, of course, exceptions if variables depend on each other, are not independent, or conditions. But in this course, you always want to have the same number of varies as achieves. Otherwise, the problem is not well posed. Okay, so vary statements tell GMAT which variables it can change. Let's configure that one first. Here I want to vary the magnitude of the impulsive burn. And as I said, I want to apply the impulsive burn in the direction of velocity. That corresponds to element 1 in the V and B axes. By default, it's already selected element 1 of impulsive burn 1, which happens to be exactly what we want. If that were not the case, we can change this variable by selecting edit and choose a different variable that GMAT will change. Okay. But since that's exactly what I want, then I just have to worry about configuring the numerical parameters here that define the range and steps. Okay, so the range is defined by the lower and upper limits. The initial value is the initial guess that GMAT is going to make to look for a solution. The step size is the maximum step size it can take. The perturbation you should never change. That has to do with calculating the numerical derivative, and it needs to be non-zero. 10 to the minus 4 works very good, so don't change it. The initial value should be, it can be the endpoint, but it's better if it's not. Since I want to increase the size of the orbit, I know this initial value should be positive. 0.5 is a good initial value. The lower limit, since I know the impulse should be positive, should be 0. The upper limit, it puts pi by default, but I recommend changing that to something like 5. Okay, so why? Because 5 kilometers per second is a large impulse. If I put 11.2, that would be enough of an impulse for an object to escape from the Earth's surface. So 11.2 kilometers per second is a really big impulse, really fast, and it's not likely you would ever need something that large. Of course, there may be exceptions, but most of the time, 5 kilometers per second is a huge impulse, and you're not likely to see solutions that require more than that. Okay, so if you need a lower limit below 0, you could put -5, upper limit of 5, but you should never include something like 50. Right? That's a ridiculously large impulse that, yes, that you're not ever going to need. Okay, the maximum steps should be enough to go across this range between 0 and 5 in 100 steps, remembering that we have 100 steps in the solver. So I could choose 0.5. It doesn't need to be exactly that. 0.1 is reasonable, 0.2 is reasonable, but this should not be 5. Why? Because then can step immediately from the initial condition to the upper endpoint, and the endpoints are numerically dangerous. The algorithm can get stuck there. If the numerical derivative asks it to go beyond an endpoint and it's already at the endpoint, it will just get stuck. Okay, so the step size should be close to the size of the range divided by the number of steps that the solver has, which is 100. I'm going to choose 0.1. 50 steps would be enough to get me across this range. Okay, so it's important to know how to configure vary statement. Many times gmat will work even if it's not configured well, but it's part of the gradient of the Therea is to configure it well, to use the knowledge that you have about the solution. Here we have the knowledge that it's going to be positive, to choose reasonable range for the solution and a reasonable step. Okay, so we told gmat to vary the magnitude of element 1. Then we need to apply that element to actually change the velocity of the spacecraft. The maneuver event associates a burn with the spacecraft. Since there's only one of each, that's automatically correct. If you want to apply it in the backward sense, you can check this box, but here we don't want to do that. If we did, we'd have to use negative values in the vary. Okay, so we apply that maneuver, and now we need to tell GMAT what to achieve in the new orbit. Here, our mag is the magnitude of the radius vector. I'm going to use the radius of apogee, which is rad apo, as the variable for the achieve, and tell gmat to achieve a radius of apogee which is larger than the radius of the Hubble, but not as large as a geosynchronous orbit, which is the value here. So something like 15,000 will give it an orbit which is approximately twice the size of the original. Okay, again, this is an arbitrary choice I'm making right now, but it's important that you achieve the right thing. You'll need to change the goal variable to the correct one. For example, we might want to achieve eccentricity of 0.2. If we did that, and I had a value of 0.2, and imagine that this is eccentricity, then the default tolerance is not a good one. By default, the tolerance will be 0.1. That's okay if the value is 15,000, but if the value of the variable you're working with is small, like eccentricity, then an error of 0.1 for a target value of 0.2 is a huge error. So if this were eccentricity, you'd want to decrease this significantly by several orders of magnitude. Okay, but it's not eccentricity now, it's radius of apogee, for which we're trying to achieve 15,000. And for 15,000, a tolerance of 0.1 is good. Okay. All right, so this target is configured. We're varying the magnitude of an impulsive burn, applying the impulsive burn, achieving a new orbit. If we want to see the new orbit, we have to propagate after that. So I'm going to insert after this target a propagate event, which will propagate exactly through one period. So I'll open this propagate event. Again, the propagator and spacecraft are correct. I want it to stop after one period of the orbit, which I'll show you how to do in a moment, but first I'll show you how not to do it. GMAT knows the orbital period of any orbit. This is an default parameter called orbit period. If I were to put this stopping condition, it looks like what I want to do. It says orbit period should be 1, but it's not going to work because orbit period is not a counter. It's not counting the number of periods. It's the value of the orbit period in seconds. So it has some value here for the Hubble of approximately 3,000 seconds. So this would be saying, don't stop this propagate until the orbit has a period of 1 second. Since that's not possible, this event will continue forever. The way to stop after one orbit period is to set the elapsed time in seconds equal to the value of orbit period, like this. Okay, so this will stop when the elapsed time of that event is equal to the value of the orbit period. So therefore, propagate for one orbit period. I'll also show you how to change the color here, one of the few things that you can manipulate in the plots. You can change the orbit color to something distinct. That can be useful if you want to focus on one particular segment of the mission. Okay, so let's run the mission now and see if this target loop works and we get the new orbit. Let me minimize this plot. Right, so, well, in the 3D view is the easiest one to see the new orbit. You can see that it's this blue one is the new orbit. It's in the same orbital plane, which is obvious by changing the orientation with the mouse. It's about twice as large, at least the radius of apogee is about twice as large as the original radius. Okay, and we could animate the mission here. We see the Hubble go around about twice, goes to perigee, which happens to be over here, and then goes around exactly once on the new orbit. When the target loop is run, it opens up an associated window here, the solver window. And if the target loop converges, this is in green and says converged. If not, this is in red. And you see the value that was achieved, 1.2884, that we asked for a value of 15,000 kilometers for the radius of apogee, and it achieved that with an accuracy of something like 10 to the minus 5. Okay, so it converged easily. This is not a difficult target. Other targets can be a lot more difficult. But once you've successfully run any target, you'll probably want to apply the corrections through this button here. So if you double click on target in this properties window, apply corrections, we'll use this answer as the initial condition for the next time it runs the mission. And that means that when you open the vary, this initial condition has been changed now to 1.288. Okay, so that makes the program faster because it doesn't need to take any steps. It already has the solution when it goes through the target loop. Also, it can be if you have multiple targets that you get irritated at seeing this window appear every time because there'll be a lot of these windows that will cover the other plots. If you're tired of seeing that, you can make it go away by deselecting Show Progress window. Then the next time you run it, you won't see the progress window. Okay? Okay, are there any questions about target loops? Again, this is a key part of GMAT. This is probably the simplest one imaginable. Okay, another thing you'll need to do in GMAT is to create your own variables. That's a resource. I mean, GMAT has a lot of variables already defined, right, which you can see a list in many places, like here. All of these variables are automatically defined, so don't create a variable if it's already there. Right, the elapsed days, elapsed seconds, the energy of the orbit. Down here at the bottom are the Cartesian coordinates and velocities, the magnitude of velocity, etc. There are lots of different variables, but it doesn't have everything, and many times you want to create your own, perhaps to save a value at some particular moment of the mission that you can use later to compare to the new one. Okay, so variables can be created in resources in the folder called variables, arrays, and strings. If we click add from that variable, it appears another window where you give the variable a name and an initial value. We're going to create a variable called AOL for argument of latitude. Argument of latitude is an angular variable measuring the angle of the orbit with respect to the equator, and it's equal to the sum of the argument of perigee and true anomaly. That's a variable which is well defined even for circular orbits. Okay, so GMAT doesn't have it by default, but we can create it. I'll give it an initial value of 0 and close. Right now, I just created a variable that has this name. It has an initial value of 0, but it's not related in any way to any other variables. And if we don't update it, it will remain at 0 forever. So user variables need to be updated within the mission. Okay, which is what we're going to do now. So remember that this first propagate was for 12,000 seconds. And that was the propagate that gave us this plot, which looked strange. So imagine I want to replace this propagate with an equivalent piece of code, but one which will also update the new variable. Okay, so that can be done with a while loop. Let's insert after this propagate a while loop. So down here at the bottom of this mouse menu is control logic. Within control logic is if else, for, and while. So I'm going to insert a while loop and make this while loop last 12,000 seconds to correspond to this. And the while loop will do two things, which will update AOL and propagate a short period of time, update it again. So it moves in steps and updates the variable. Okay, so first I want this while loop to exit after 12,000 seconds. So I'm going to make the exit condition not elapsed days, but elapsed seconds, less than 12,000. Okay, so this is the exit condition for the while loop. Within the while loop, as I said, we need two events, which are an equation that will change the AOL variable to be equal to argument to perigee plus true anomaly, and after that, a short propagate. Could be before as well. Okay, so first we'll do the equation. In the equation, you set something on the left-hand side equal to something on the right-hand side. On the left-hand side, we want AOL, the variable that we created. Unfortunately, there's no list here to select from. You have to type it by hand. And the variables in gmat have a long name. The first field is the name of the spacecraft. The second field is either the name of the central body or the coordinate system. Here, for argument of perigee, we need the coordinate system, which is called MJ2000EQ. And finally, the more intuitive name, ALP, for argument of perigee. Okay, so you have to type this full name. That's the argument of perigee. And we add to that the true anomaly, which is Hubble.Earth. In this case, it's just the central body, not the coordinate system in the second field, and TA. Okay, since those are long names, I click apply first. If I had made a typo, it would give me an error message now. Okay, so just point out that if you can't remember these names, which of course they are difficult to remember, you can access them from any of these lists. Here you see the full name of elapsed seconds is Hubble.elapsed seconds. If I wanted the full name of argument of perigee, I could select that, and here on the right you see the full name, which is the one I had just typed. Okay. I'm clicking cancel because I don't really want to change this propagate event. Okay, so we have this equation that will set AOL equal to the sum of those two angles, and we want to propagate a short time. So we can do that by just changing the 12,000 in the stopping condition to 60. Then this propagate will go for 60 seconds. Okay, so this while loop will do the same thing as this propagate for 12,000 seconds, while updating the user-defined variable AOL. However, we're not going to see that variable anywhere because we haven't included it in any outputs. If I include it in the definition of this XY plot 1, then we can see it and compare it to these two variables. So we can do that by clicking Edit Y from the definition of that output. And we have to find AOL. GMAT organizes parameters and variables into object type. There's an object type for spacecraft, space point, impulse at burn, array, we won't need, and variable. If I select object type variable, then we would see a list of all the user-defined variables. The only one we have in that list is AOL. With this arrow, I put it in the list of selected variables to show in the plot. Okay, so now we have added AOL to this plot. If I click OK and run the program again, and we look at this plot, we see the results. So AOL, remember, was 0 because we set it to 0 for its initial condition, remains 0 for 12,000 seconds. Then when we get to the while loop, it gets updated. We see it change linearly, which is good. All right, that's what we wanted to do. However, it jumps in strange places and has values larger than 360. That's because we're adding two variables that individually can be between 0 and 360. Their sum can be as large as 720. That doesn't really make sense since this should be an angular variable. So we can fix this problem with another equation or something called a script event. So that's what I'm going to add now. Script event you need to know how to use in general. So insert after this equation a script event. Script event has a series of gmat commands, and it's a nice way to do lots of things at the same time instead of adding multiple equations. Right? If you need to set 5 things equal, it's yes, it's a bit messy to have equation 1, 2, 3, 4, and 5. In a script event, you can do it all together. Script event is a window like this where you type gmat commands. Okay, so first thing I want to do is copy this command in the equation, but in the gmat syntax. That I can get from the script if I click Save here and open the script again, which we haven't done this in a while, so it's also interesting to see what gmat has changed. We defined the Hubble spacecraft. That section is here. We have the force model for the propagator J2. We have the impulsive burn. That's a new section that we created. We have a solver, which we created. Subscribers, the two plots, and the XY plot, and the report. And down there's the variable here, and down there at the end is the mission sequence. So within the mission sequence is the while loop, which is here, the target loop, which is here, and within the while loop is this line, which corresponds to the equation. This sets AOL equal to AOP plus TA. So I'm just going to copy that and paste it here. And for some reason that did not copy correctly. Let me see if it'll work this time. Okay, so that saves me the time of typing this again. And at the moment, this does exactly what the equation does, but if we add another line, we can take the modulus of this angle and not allow it to exceed 360. So AOL equal to mod AOL 360. GMAT commands must begin with GMAT in capitals and end with a semicolon. Okay, so these two things together will force this angle to be between 0 and 360. Notice that I typed MOD for modulus. GMAT has a number of basic commands, sine, for example, SIN, cosine, absolute value, ABS. Basic commands like that are what you would guess based on experience with MATLAB. You can see a list of these in the user manual, but again, basic functions are automatically defined. All right, so I'll click OK here. Now this script event repeats what was done in the equation, so we don't need the equation. Delete that. And this script event will then force this angle to be between 0 and 360. So let's run this again and see if that is the case. And now the blue curve, which is AOL, stays between 0 and 360. You notice that GMAT doesn't automatically change the scale of the axes. If you wanted to do that, you need to close the window and force it to redraw the plot. I accidentally clicked animate instead of play. Once I click play, it redraws this plot and rescales the y-axis. Okay. Okay, so I'm going to continue manipulating this plot a bit. AOL is behaving well, but you'll notice that in order to see the behavior of this variable, we really only want to see this. Okay, sorry, the audio disconnected for a moment. To see this variable here, we are really only interested in this section of the mission here. That is, we're not interested in the initial 12,000 seconds, nor what occurs after the target loop here. So it makes more sense to make this plot focused on this period of the mission only. And in any case, you do need to know how to control the outputs to plots. So let's do that now. The plots to, or the output to plots and other outputs can be controlled in the mission with things like pen up and pen down, which are here, or toggle. Pen up and pen down, well, pen up will lift up the drawing pen from the plot, that is to stop drawing. Pen down will put the pen down again, begin drawing. Toggle is a switch that can turn on and off outputs. I'm going to use toggle here. Put one before the while loop, one at the very beginning of the mission, and one at the end of the while loop. Okay, so what I want to do is turn off this plot in the beginning, turn it on before the while loop, and turn it off again after. So first open the toggle at the beginning, and we want to turn this plot off. Select action off, deselect the plot that's selected by default and select XY plot 1. That turns it off. Turn it on again just before the while loop, and turn it off again after the while loop. Okay, if we run this again, we should only see this section of the mission. Okay, which is what we see. If we wanted to resize the axes, close it and run it again. Okay, so this is a good plot now for comparing or looking at the behavior of this variable AOL. You can see these steps here that correspond to 60 seconds. We could reduce the size of this propagate event in order to get more resolution there. Okay. Okay. Right. Next thing is report files again. The reason is because, as I mentioned, there are two ways that we'd want to use report files, but we only used them in one sense so far, which is to record the data for the mission. So report file 1 is going to have long columns of data. Looks like this. Some of this data corresponds to the first orbit, some to the new orbit. Okay, so another useful way to use a report file is to use it as a type of scratch paper or a way to organize information or answers. That is, it's a nice way, for example, to organize the answers to the questions that I will ask you in the tarea. Right, if I ask you, what is the value of the impulse you used? You can just get it from the window, but other answers might be more complicated, and you can always write them to a file in gmat and have a nice organized file. Another thing is to debug your program. If your program is not giving you the answer you expect, you can test the value of specific parameters at specific points and therefore check if it's doing what you think it's doing. Okay, so to do that, you can use report as again, a type of scratch paper that you write to at specific points. So let's create another report file 2, and make this an empty file unless we write to it. To make an empty file, you have to remove the parameters that are in the parameter list. If I remove both of those, so it's an empty list, and run the program, we will see an empty file as report file 2. Okay, so an empty file won't help us, but we can write to this using a report event at specific points of the mission. For example, imagine that I want to remember the value of the impulsive burn that we used in this target. After this target, I could put a report event and tell it to write the value of the impulsive burn to that empty file, report file 2. So I choose report file 2. The parameters in this report event are just going to be written at this particular moment, not for each time step. And let's choose the value of those impulsive burns elements, which we get by first choosing object type impulsive burn. Impulsive burn 1, first remove the default parameter, then select element 1, element 2, element 3. Okay, so this event will write those 3 elements to report file 2. Click OK. If I run the mission again and open report file 2, we see those 3 values. Of course, elements 2 and 3 are 0 because their initial condition was 0 and we never changed them. But element 1 has acquired the value that was calculated in the target loop, 1.2884. Okay. Okay, so again, this is a useful way to organize answers, for example, or to debug your program. And basically the last topic today we're going to talk about is clones. Okay, so this file we don't need anymore. We have already done one short test of removing the J2 effect and looking at how the 2 angles, ran and true anomaly, behaved with and without it. But in general, one of the things that is useful to do in gmat is to look at the effect of different perturbations. Okay, so that can be done by changing the values of the propagator here. Right now, this propagator includes J2, the moon, and the sun. I could remove the moon, for example, rerun the program and look for differences. How do you look for differences? Well, you could save the data and open different sets of data in a different program. But if you want to do it directly in GMAT, it's not so nice because you have to do a screen save or somehow remember what it looked like before. To compare directly in GMAT, you can use something called clones, which is essentially to make multiple copies of the spacecraft, to propagate them in slightly different ways, and then look at the difference between those curves in the same plot. Okay, so that's useful, and show you how to do that now. First, let me close this window. So the spacecraft has an option called clone, which is here. If you click clone, it will create a copy of that spacecraft. We can do that twice here. Again, this copy will have the same initial conditions as the original spacecraft. And then I want to propagate these three spacecraft, or one spacecraft and its two clones, with slightly different propagators. The initial propagator we have is J2, and I want to create two new propagators, one that doesn't have J2, that treats the Earth as a point mass, and one that includes J3. The clone option for propagators is not yet enabled, so we have to configure them again from scratch. Let's add two new propagators. First, I'll give them names. I also forgot to mention that one somewhat irritating bug in GMAT is that the rename option and other things disappears sometimes from the right mouse menu. It doesn't mean that you can't rename. The shortcut for rename is F2, which is always available, but you won't see it again in the mouse menu unless you close and restart the program. Okay, so this propagator I want to be prop point mass, and we'll treat the Earth as a point mass. This propagator I'm going to rename prop J3 because we're going to include also the perturbation J3. Okay, so now we need to configure these. Prop point mass. Well, first I'm going to choose exactly the same parameters for the numerical method as we did in the first one. Brainstorm 780. And here I want to treat the Earth as a point mass, which means I want degree 1, order 0. To be the same as before, I also need the moon and the sun. Okay, so this propagator is exactly the same as before, except that we've removed the J2 effect. One other thing I forgot to mention is the model here. The gravity model is essentially a model of the Earth's shape, which is used to calculate coefficients. There are two models here that are the most common, JGM2 and JGM3, stands for Joint Gravity Model. What's important is you don't confuse this 2 and this 3 with J2 and J3. So for us, it doesn't matter which one of these we use because we're using just a small number of perturbations, and the coefficient values will be exactly the same for these models. If we use higher order, there could be some small difference between these two models. Okay, because again, they depend on the precise shape of the Earth, which can be different in these two sets of measurements. All right, so again, to summarize, this propagator treats the Earth as a point mass, but is otherwise identical to the first one. Propagate J3 should again be identical to the first one, except for the fact that we're going to include J3, which we do by having degree 3 and order 0. I also need the moon and the sun to make this the same as the previous propagator. Okay. All right, so now we have 3 propagators and 3 spacecraft. And we could compare the behavior of whatever parameter we want between this spacecraft and its 2 clones to examine the effect of perturbations. Okay, so perturbations normally have a slow effect that causes the parameters to drift, but it takes a significant amount of time to see a substantial change in the parameters. So I'm going to integrate for 10 days, which is long enough to see some change, by changing the stopping condition of propagate 3 from 1 orbit period to elapsed days equal 10. What I want to change is here, elapsed seconds equal to elapsed days, and then choose a value of 10. Okay, so this propagate will stop after 10 days. And shouldn't close it because so far this propagate is only acting on Hubble. If I want to compare the Hubble and its two clones, I need to also act on those clones. Okay, so propagators can be associated with multiple spacecraft. For example, if I want propagator J2 to act on Hubble and its clones, I could select them from this list. Let's just select one, click OK, and you will see them here separated by commas. So you can propagate multiple spacecraft with the same propagator, but you can also do it with different propagators by placing them on different lines. So first I'll remove Hubble 2 here, so that it will allow me to use it on a separate line. On the next line, let's associate prop point mass with Hubble 2. And on the third line, we associate prop J3 with Hubble 3. Okay, so these three lines have different propagators acting on different spacecraft. If you do that, you need to choose propagate mode synchronized. That forces GMAT to take exactly the same time step for all of these spacecraft. Without that condition, it is permitted to take different time steps, and it will probably do that, which means that the spacecraft won't be synchronized, and the plots, if you're looking at multiple spacecraft, will look very strange because they don't have the same mission time. Okay, so choose synchronized mode whenever you have more than one line here in the propagate event. And then also, if they're synchronized, it doesn't matter which spacecraft you refer to in the stopping condition because they have exactly the same elapsed days, exactly the same mission time at all times. Okay, so now this propagate will show the three spacecraft. Let's run this again after we create a suitable output. So right now, we haven't decided what variable we want to compare between these clones. Let's create an output that will look at the RAN value. So I'll create another XY plot called XY plot 2. Open XY plot 2, and on the x-axis, I'm going to choose elapsed days, since we're propagating for 10 days. And on Y, remove the default variable and find the RAN for all three spacecraft. First Hubble, then Hubble 2, then Hubble 3. Okay, so this plot will compare the behavior of these different propagators um, in terms of its RAN parameter. Okay, so now let's run it. And we see this new plot here. By the way, GMAT is much faster if you minimize plots like the 3D orbit view. It takes it a lot of memory and time to redraw points on a plot, and it's useful to minimize them or even delete them if you don't want to see them. Okay, so this plot shows us the difference between RAN for these three spacecraft, which are really the same one, cloned twice. The one that treats the Earth as a point mass is this green one, and you can see that for that spacecraft, the RAN value is almost constant. It changes a little bit, again, because of the moon and the sun. But it's very, very close to a constant, which is what you expect. The red one treats the J2 effect. For that, the RAN value increases almost linearly. It's drifting. And the blue one drifts at a different rate. This doesn't really make sense because these orbits are or these spacecraft are supposed to be clones. But the thing that's wrong here is that we forgot that the mission is acting only on the original spacecraft, which is the red one. So this mission changes the orbit of the spacecraft. So the red one is in the new orbit with a radius of apogee of 15,000. The blue one, however, is in the initial orbit because this mission does not act on that clone. Okay, so if you want to compare the effect of different parameters, you need to make sure that the clones are synchronized with the original spacecraft at the moment you're going to compare them. And that's what we have not done here yet. So prior to this propagate, which is the propagate that compares them, we should synchronize them. That can be done with a script event. So prior to this propagate, I have a script event which will synchronize the two clones. So I can do that with gmat Hubble 2 equal to Hubble. It synchronizes Hubble 2 with Hubble. The same line with 3 instead of 2 will synchronize Hubble 3. This is a much more convenient way to do it than doing it one by one. Remember that spacecraft have a lot of individual parameters, which you can see here. Right, so you could figure out which ones of these are different, basically the orbit parameters, and change them one by one with different lines in the script event. But if you simply type the name of the spacecraft without any additional fields, it will change all of them. So these lines will synchronize the spacecraft at that point. So the clones are exactly the same, and therefore in the new orbit as Hubble. Okay, so if we do that, then this plot should look better. Now we just see two curves, the green one, which treats the Earth as a point mass, and the red and the blue one are nearly identical. We can zoom in on that, and you see the difference between the red and the blue curves is really, really small. So what conclusions can we draw from this? The moon and the sun are having a small effect on RAN. That's visible in the green curve that changes very slowly. We can't distinguish between the moon and the sun because we're treating them together, but both of them have very small effects. The red and the blue curves are nearly identical. That means the difference between treating the J2 effect and treating the J3 effect is negligible. Since both of those include J2, the difference is whether or not J3 is present, we can conclude that the effect of J3 is negligible. Right, because the difference between these two curves is the difference due to J3. They each include the effect of J2. So we conclude that the moon and the sun are not important. J3 is not important. J2, however, is important because that's the difference between the green curve and the red and the blue ones. Okay, one final thing we could do to make this plot even better is to turn off the plot during this initial period where we're not comparing the clones. That's easy enough to do by including that plot in the off switch in the beginning and putting another switch before propagate 3, which will turn on that plot. On, deselect the default, and select XY plot 2. Then I'll close this plot to force it to redraw the axes and show it one more time. Okay. So finally, this is a good plot that allows us to conclude something about which perturbations are important for RAN, at least considering J2, J3, the moon, and the sun. Okay, there are various other things that I haven't showed you how to do. There are resources that we will use in the next two exercises, like ground stations, which you can add here. Okay, again, we'll do this in the next exercise. There are event locators. Eclipse locators calculates eclipses. Contact locators calculates contact between ground stations and specified spacecraft. We'll do both of these things on the next pratica session. And in the mission, there are a few other things I wanted to mention. There is something called a stop event. So for example, I can insert before this while loop a stop. This will stop the mission before that while loop. So if I run it now, I won't see this plot because it doesn't get there. So stop events are useful to stop the mission sequence and help you debug it. For example, if you've added a lot of new things in the mission and it doesn't work, you want to go through one by one and see which one of them is the problem, you can move the stop progressively further down the mission. A similar thing is the, is it here, breakpoint, which will also stop it and pop up a window with some information. You can mark a point in an XY plot if you want to see the exact point where the maneuver was applied. That point in the data can be marked with an X or a flag and using mark point. Yes. So there are other things there you can play around with, but the ones that we're going to need in the practica, we've already talked about. Well, with the exception of ground stations and event locators that we'll talk about more in the next two sessions. Okay, so I didn't mention that there was a section on finite burns that I'm not going to go through. So basically this covers all the things that I want to cover today. Are there any questions? Let's stop event here. Okay. I mean, we finished 5 minutes early. That's fine. If there are any questions, I'm happy to talk more right now, but if there are no questions, then I'll see you in the next practica session. Okay, it seems like there are no questions. So in that case, I'm going to end the session and we'll see you next time. Hasta luego.